Hi, welcome to my channel JaberTime. Today I'm going to cover another topic in Calculus 1, integrals of even functions, integrals of odd functions, and average value of a function, with some examples. Integrals of even and odd functions. To get you started, I'm going to talk about the even functions. We'll move on to the odd functions after. And I'm gonna also start with an introduction. I know this is calculus, you should know what is even function and odd function, but it doesn't hurt to take a few minutes. I'll go a little bit quick and show you what's even and what's odd. Introduction. The best example to start with is called f of x equals x to the second. It's called an even function. And this is how it looks like. If you notice right here, 1 takes you up to 1, negative 1 takes you up to 1 also. In general, x takes you to f of x, but still negative x, which is on the other side of the y-axis with the same distance, takes you also to the same output. F of negative x is up here, f of x is up here, and they're both leveled the same level. Here's another example, a good number. 2 takes you up to 4. On the other side, negative 2 takes you to 4 also. This is called even. And since this is not really a calculus detailed topic, I'm not writing everything, I just want to remind you. We say that even functions are symmetric about the y-axis. Pretty much you could see that right here. Formally speaking, we say f of negative x, like negative 2, is identical, the same to f of 2. F of negative x equals f of x. So sometimes you have a function and they say verify algebraically that this is even or odd. All what you need to do is plug in negative x into the function f, simplify. Once you finish, compare to f of x. If it's the same, we call it even. So the same graph, but just to give you the concept quick, take x, negative x, the outputs, how far you go up, it's the same value. Usually even functions, they're not always y equals x to the second or similar to y equals x to the second. They could be absolute value. I know we call it even, but probably they start with the even because it relates to x to the second. So that is symmetric about the y-axis. As you can see from right and left, it's the same values. And here's another example. Y equals negative x to the second plus 1. Upside down because of the negative. The leading coefficient is negative. Opening down. Shifted up 1 unit, and that's why it looks like this. Still similar. The similarity is happening about the y-axis, which I'm not writing here because, as I said, it's just like an overview. It's an introduction. So one more time to support what I'm talking about, even functions, they should follow this condition right here. I think that's good enough to get started about even, and I do have more examples or more graphs to help you understand more and more. Let's go to the second keyword, which is odd functions. In odd functions, we'll start similar way with an introduction. The best example, what do you think? Earlier I took the best example for evens is y or f of x equals x to the second. So for odd functions, it's gonna be x to the third. Yes. How does it look like? Looks like this. 1 takes you up to 1. Negative 1 doesn't take you up to 1. It takes you down to negative 1. 2 takes you up to 8. Negative 2 doesn't take you up to 8. It takes you down to negative 8. So we don't have a similarity about the y-axis. We have a similarity about the origin. This is across from the origin to the other side with the same distance. This is across from the origin to the other side with the same distance. So if you graph a line that goes through this point and this point, you're going to go through the origin. All right. Similarity about the origin for odd, similarity about or symmetric about the y-axis for even functions. In short, that's how it looks like. X takes you to a value called f of x, but on the other side, negative x doesn't take you to the same value, takes you to f or down to the bottom side to make the symmetry about the origin. So in evens, we use the word same. Here we don't say the word same, we say opposite. If this is 8, this is opposite negative 8. They don't have always to be x cubed. This is y equals x or f of x equals x. Just simple as that. As long as the symmetry is happening through the origin, we call it odd function. So to summarize that algebraically, this is what we have. Notice that I wrote the negative sign in red to highlight that, to say that f of x and f of negative x are opposite to each other. It doesn't matter if you write the negative here or here, of course. As long as you get the concept that they are not the same, they are opposites, we call it odd function. Now, odd and even don't have also to be polynomials or absolute value or straight as y equals x. They could be trig functions. Here is one. Sine x is graphed from negative 2 pi to 2 pi. Do you think this is odd or even? Is it symmetric about the y-axis or about the origin? It's about the origin. You see this right here? This point is reflected here. This point is reflected here. This point is reflected here, and so on. This point is reflected right there. So what do we call this? We call it odd function, and we use the word opposite. Here's a cosine function, graphed from negative 2 pi to 2 pi. Do you think this is symmetric about the y or about the origin? Odd or even? Even function, similarity. You see pi over 2 to the right, pi over 2 to the left, which means negative pi over 2 has the same outputs. They're leveled at the x-axis, so they are the same. 2 pi is up here, negative 2 pi is the same thing, same level, up to 1. Even, odd. So, do we have the functions always even or odd or something else maybe? No, they're not always even or odd. They don't have to be always either symmetric about the y or symmetric about the origin. They don't have to. So when it's not the same or neither, they don't equal the opposite and they are not the same, we call it neither. So that to support algebra, when you start solving or simplifying, you go like, they're not opposite, but still they are not the same. So we call that neither. Some examples quick. This is neither. This is a cubic. I know we called x cubed odd, but not every polynomial of third degree is odd. This is a good example. If it's shifted up 3 units, I don't see a symmetry about the origin anymore. Here's another example. This is a second degree but shifted to the right 2 and up 1. That's not symmetric about the y or symmetric about the origin. So yes, we do have functions that they are even, functions that they are odd, and sometimes neither odd or even. So let's summarize, going back to our topic. What is happening with even and odd functions with integrals? This is what we need to know. If you have an even function symmetric about the y-axis, it looks like if you want to go from negative a to a, negative 5 to 5, negative 4 to 4, same distance to the right as to the left, the areas under the curves are symmetric. Which means if I want to integrate from negative a to a right here, I could just reduce my work and go from 0 to a. Once I finish, I double it. You might say, why do I need to do this? For many reasons. Sometimes it's a lengthy process, and to plug in numbers like a and negative a in all of them, like f of b minus f of a, if you remember, sometimes it takes more time. So when you get to plug in 0, you don't have to plug in 0, it's just like 0. So that's one benefit. Besides, I would say another benefit is the more that you know, the more that it's gonna help. Skills, practice do help a lot as you move on in math. So keep that in mind. What about odd functions? Odd functions, if you graph it and look at the area, always the area is with the x-axis. So if you're above the x-axis, you're gonna get a positive integral value when you integrate, because you're above. Remember the base times height for Riemann sum? Here the heights are not up, they're down. So by just applying the math, you're gonna get negative number. Well, what happens with odd functions, if you go from negative a to a, this is gonna be a positive number, this is gonna be a negative number. If you don't look at the graph and you add them up, you're gonna get 0, as you can see. See, I'm trying to highlight that and making it like a larger font with a different color, as I'm trying to highlight this with this right here. So this is a summary of the topic of even and odd. Then once we finish, I'm gonna go to the average value, then I'll do some examples with you. Let's look at some cases that you have to be careful. And as I said, the more that you know about things, the more that you're going to be careful and avoid making mistakes. We know that this is odd, that's a sine function. We know this is even, that's a cosine function. This is the main algebra formulas, if you want to call it algebraic formulas. Opposite, same. This guy right here, odd function gives you 0. We know this, right? You go to the right, that's what you get. You go to the left, that's what you get. This and this balances, but they cancel each other. One positive, one negative, they cancel each other. You go halfway, cancels halfway, and similar concept. Now for even functions, I know the general rule says twice from 0 to a. You could do that, but if you know that we have some kind of symmetry, you could reduce your work and just find the answer quick. I'll show you what I mean. Instead of going from negative pi to pi, negative pi to pi, and I know that it's even, and I say, oh, you know what, I'm gonna go from 0 to pi and I'm gonna multiply by 2. You could do that, but you're gonna finish with 0. The 0 here is not highlighted. It's not something that we should pick quick from the rules, but take a look. Negative pi to pi, negative pi to pi. This is positive, this is positive, this is negative, this is negative. Because of the symmetry, they're gonna cancel each other. Do you see that? It's not because it's even they cancel. Odd they cancel. Odd is a rule, they cancel. The even function, it could be 0. I mean, it doesn't have to be like always like 7 and 2 and a number. For some reason they cancel. If you go from here to here, they're not going to cancel. So just be careful, and as I say, the more that you know, the more that you could get your answers quicker sometimes and with less work. I'm gonna keep supporting that till I get to the average value function. Even functions, they say same. From negative a to a, you could go from 0 to a and double it. That's the even functions. So let's just take care of negative pi to pi and say what is 0. Why it came up to be 0. Here's my function, the cosine function. We're gonna go from negative pi to pi. So I have the function right here, negative pi over 2 to pi over 2. From here to here, that's not gonna be 0. But this one here, from negative pi to pi, as I mentioned, this will cancel this and this will cancel this, and you end up with 0. But is it always 0? No. For even functions, it doesn't have to be 0. It could be any number. 0 is just like a number. So in this case, came up to be 0. In this case, it's not going to be 0. I could tell from here to here, this is positive, positive. They're going to add up to a number, and the answer is 2. So let's see how we can get the 2 with our notes for this topic. The idea is you integrate. That's one way to do it. The derivative of sine is cosine, which means the integral of cosine is sine, going backwards. I'm gonna plug in A and plug in B, just like what the fundamental value theorem says to me. And I'm gonna go straight forward, connect this section to last section, plug in B, plug in A. After you integrate, sine pi over 2, to remind you where is that, it's up here 1. Sine negative pi over 2 is down here negative 1. 1 minus negative 1. Answer is 2. Now we are in a topic that's not called fundamental value theorem, it's called even functions. So I'm gonna use the even functions concept. Cosine is even, and we're going from the same amount to the left to the same amount to the right, negative a to a. So I'm gonna use the concept of 2 times from 0 to pi over 2. One more time. The integral of cosine is sine, because the derivative of sine is cosine. I'm gonna leave the 2 out of my way. Go from 0 to pi over 2. Plug in pi over 2 first. Plug in 0 next. Subtract as the fundamental value theorem part 2 says to me. And sine pi over 2 up here, which is 1. Sine 0 down here, which is 0. 2 times 1 minus 0 is also 2. Alright? I think that should be enough to understand what's even and odd functions and what this section tells me to do it with integration 2 times. Alright? Let's go to the average value of a function. What does it mean? The average value of an integral function f on the interval from a to b is, we write a bar on top of f, we call it f average, 1 over b minus a multiplied by the integral from a to b f of x dx. Sometimes we see formulas, we don't believe in it much, we practice and we use it. Sometimes we go farther and we understand what does it mean, why there is a 1 over b minus a in the front. And it's worth it sometimes to take some time and look at it and understand the concept behind it. It's not really something huge that it's going to take my time to display for you, so I'm going to do it. Here we go. First of all, the average is the following. You could see this graph is going up this way, so f of a is the lowest, f of b is the highest, and the average of f values will be somewhere in between. It's kind of like symmetric, somewhere here. Alright, now sometimes they call it f with a bar on it, sometimes they say f with a small index called avg or ave, whatever they want to call it, f average. Alright, now this here is from a to b and y is f of x. So I'm gonna go from a to b and y is f of x. If I do the integral from a to b under or of f of x dx, I'm looking for the area that is under the curve from a to b, which is kind of like this shape right here. That's called net area. Alright, you know, integration gives me the net area, but whatever that is, you could change it to this much, the rectangle. You see that? This much I'm losing. If I go up to this level and make it straight horizontal, I'm losing this part. But it looks like somehow I could look for the point, the exact point that this and this balances each other. So what I'm losing here, I'm gaining right here. You get my concept. So what is the height that balances this back here? And that's called f average. Let's look at the rectangle. Area of a rectangle is base times height. The base times the height up to here, and base is b minus a, and the height we called it f prime. So far so good. base times height. Okay, but the net area is an integral from a to b f of x dx, meaning I could do the connection, tell that this much, the area of the rectangle, is similar to the net area under the curve. Doing the math, getting rid of this out of your way, having f prime by itself, you're going to divide both sides by b minus a, and now you have it. That's the formula. Here, if you want to start from here backwards, multiply both sides by b minus a, you see it here. b minus a is the base, and f prime is the height. A quick example, I'll just say something quick. If you go from, let's say, point A to point B, and it takes you 2 hours, and somebody says how long it took you driving, and you say, oh, I drove from 5 p.m. to 7 p.m. exact. So it took you 2 hours, and let's say you say that I covered 150 miles. Well, you know, and it's common sense, that on average you are driving 75 miles per hour. But were you driving 75 miles per hour every single second? No. Sometimes you slow down, sometimes you go higher than 75. On average, as a rectangle, it's like you went straight, fixed speed, 75 miles per hour. I think that should help to understand more about the average. So it could be higher in some cases, lower some cases, but if you want to build a rectangle out of it, like from 5 p.m. to 7 p.m., I'm going like 75 miles per hour, I will cover the same distance, because this is called distance or displacement, alright? If you remember those applications. Alright, let's move on. We have x to the second, and we're going to go from -2 to 2, from -2 to 2. That means this area right here, and this area right here. This is just to remind you know what's going on with the even functions. And we're starting with examples. We could apply what we learned, take the 2 out as twice from 0 to 2. X to the second, integrate, you erase the exponent by 1 and you divide by the new exponent. So it becomes x cubed over 3. We're going from 0 to 2, and we apply f of b minus f of 0, or a, multiply by 2, and we get 16 over 3. That's how we do it, or apply what we learned in this section. Let's take an example of an odd function. So simple. This is the simplest one ever, and here's the simplest one for cubic. This is how it looks like. We're gonna go from -2 to 2, and this right here is gonna be symmetric to this. This is gonna be positive, this is gonna be negative. Now, what do you think the answer is gonna be? Should I integrate? Should I take my time and calculate? I don't think so. This is what I call it, like the more that you know, the more that you're gonna have more skills and more knowledge, and you're gonna be confident and go faster than others. Here's the answer. That's it. I'm done. Alright? Hopefully that's clear. It looks like I'm repeating myself a lot. Odd functions, if you go from -a to a, you don't have to waste your time. It's going to end up 0. It's a fact. Alright? Let's try something else. All the way from -2 pi to 2 pi. I know this is even, symmetric about the y-axis. Should I go from 0 to 2 pi and multiply that by 2 and finish it? We can, because the integral of cosine is sine. We know this, and we could just finish it. But if you look at it, whatever I see right here is, because of the symmetry, they're going to cancel. Take a look. If this is positive, whatever that amount is, let me just assume things. It's not going to be accurate, trust me, but let's assume. Imagine if this portion right here is 5. I think this is also 5, which means this is a 10 value, and this is a 5, and this is a 10 value, and this is a 5. The lower one is -10. if you don't pay attention to it, it's area under the x-axis. So this is going to be negative 10. This is 10. They're going to cancel. This is negative 10, but there's a 5 here and a 5 here. They're going to cancel. You get my point. So what's the answer for this? The answer is 0. Alright? So you don't have to integrate. If you know enough about what I just said, sometimes with confidence you don't have to waste your time and integrate. Let's take another example. This time it says use symmetry to evaluate the following. The integral from negative 5 to 5 of x to the 9th dx. Well, x to the 3rd and x to the 9th are so similar. The main difference is like how steep it goes. Alright, how fast. But they look the same, trust me. Knowing that and knowing this is odd, but do you think the answer is going to go? Because I'm going from negative 5 to 5. I'm not going from negative 5 to 6. I'm going from negative 8 to 8. Same amount to the right, same amount to the left. The answer is 0. Done. You don't have to do anything. A different one which is more interesting. This one is interesting. Use symmetry to evaluate the following. Well, if you take your time and graph it, you will see the symmetry. X to the second by itself is even. Sine x by itself is odd. As a product, it's gonna end up even or odd. It's gonna end up odd. The idea of same and opposite, this is gonna keep everything the same. This is gonna make it odd or opposite. So the whole thing, the opposite is not gonna cancel. The word opposite is gonna stay. So we say f of x equals x to the second sine x is an odd function, and I'm boxing it to show you that as a package it's odd. Alright, you could test it algebraically, but plug in negative x, simplify, and end up with as opposite or the same. But trust me and pay attention to things like that. Kind of like tricky a little bit, but it's odd, which means we're going from the same amount negative pi to pi, and the answer is 0. Here's another interesting one. We don't have also always to focus on simple ones, so here's an interesting one. X to the 9th minus 3x to the 5th plus 2x to the 2nd minus 10, and you're going from negative 2 to 2. The interesting part about this is not a product like the previous example, but you could break it down. You know that. The integral of the sum is the sum of the integral, and so on. This is odd. This is odd. This is even. This is even. Negative 10 is a horizontal line, symmetric about the y-axis. So by knowing that, this is going to go away. That's going to be 0. That's going to be 0. I don't have to worry about them. I'll just worry about these and integrate them, and that's it. 2x to the second minus 10. I took them back. I don't have to keep them separate. There's no need. From negative 2 to 2, that's an even behavior. I'll apply what we know twice from 0 to 2. Why would I integrate and plug in 2 and plug in negative 2? Takes more time, right? So that's another benefit knowing this, and you just go from 0 to 2, multiply by 2, do the math. You know how to do this. 2 here becomes 3 divided by 3, minus 10 becomes minus 10x, plug in 2, plug in 0, becomes what's called in math capital F of B minus capital F of A, twice that, and the answer is, looks like I'm repeating myself here, sorry for that. The answer is 32 over 3 minus 40 simplifies to negative 88 over 3. Alright, now let's talk about the average value of the function. The average value of the following function on the given interval x minus x to the second on 0 to 1. Remind you of the average value rule. F average is 1 over b minus a times the integral from a to b f of x dx. Alright, we know what's a, we know what's b. We'll just put them in. 1 over b minus a from a to b. We put f of x in. That's a 1, so just to reduce our calculations. And we know how to integrate this, and then plug in 1 and plug in 0. Just simple math. I mean, it's just like application and nothing to worry about, but believing in this as being called the average. This is how we integrate. Then we go and plug in 0 to 1. This reduces to 1. 1/2 minus 1/3, and nothing to worry about plugging 0, because 0 will cancel everybody, and the answer is 1/6. Now let me support that by understanding also what is happening with this problem as a concept, as a graph. This is what we have. If you graph this and you factor it, you know the x-intercepts, and you know it's upside down parabola and so on. They want me to go from 0 to 1, from 0 to 1. Those are my x-intercepts. Instead of integrating from 0 to 1, or sorry, integrating from 0 to 1 will give you this whole area as called net area. If you want to build a box right here, a rectangle, I don't think to take the same area, you're going to have to go all up here, because that's going to be too much. And if you go only up here, that's going to be like little than what we want or less. So somewhere here, you're going to stop, and the answer was 1/6 for the average. And this is how it looks like. This point, I did the math halfway, it's called half, it gave me 1/4. And this 1/6 is somewhere there. It looks like, yes, up to 1/6, if you box it, what you lose here is what you gain right here exact. And that is the average value of the function with the graph, right? That should do it for this video. It's about 30 minutes, 32 minutes, and thank you for watching. One more video after this, and that should cover for this course, Calculus 1. If you like this video, as I always say, hit the like button, subscribe if you did not do subscribe yet, and in the coming semester I'll be adding more videos to Calculus 1 playlist and calling them part 1, part 2, part 3, just like in movies. I want to thank you and appreciate that you're staying with me to the last minute in this video, because if you're listening to me now, that means you are watching the whole thing, which is great for me, and any support will be appreciated. Next semester, which is going to start in 2 weeks, I'm going to start Calculus 3 and College Algebra. So I'll have the main 2 playlists coming. I have more actually than that, but the main 2 playlists are Vector Calculus or Calculus 3 and College Algebra, and also some stats and some integrated math 3 from high school. Thank you, and I'll see you in the next video, which is going to be also recorded tonight. So I'm uploading after this video another video for Calculus 1. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.